the RStudio screen? Great. All right. So welcome. Glad everyone is here today. I've said it a few times, but it is always worth repeating at the outset. Go ahead and grab the code for week 5. It's on the week 5 channel. So there's actually, I think, 4 different things there. There is a code for today that we're using. There's the updated HSV file. And so over different weeks, there have just been different additions I'd made, mainly like the addition of a student ID. So I uploaded that to week 5. So if you want to grab that. And then there are 2 papers on dominance analysis there. And so the reason that's there is that, as I was thinking about kind of what people were asking for in terms of thinking about analytics, we only have 4 weeks. Each of these is an hour. It's not a lot of time. And you have entire semesters that are dedicated to regression, and entire, specifically single level, and also entire semesters that are dedicated to multi-level. And there was a good mix of people who said regression or multi-level. And so the way I'm thinking about this is 1 to 2 weeks on kind of the basics and then some advanced regression analyses, and then 2 weeks on multi-level models. I think we can do multi-level models, at least covering ground on using the LME4 package, both for linear mixed models, generalized linear mixed models, interpretation, diagnostics, all those kinds of things. I think we can cover over 2 hours. So today, really what I want to do is be able to kind of show some basics and advanced aspects of doing multiple regression in R. And so we're really going to cover everything from kind of the basic diagnostics of what people would be recommended to do for regression. And so how do we think about plots? What are some of the main analyses? What are ways that we can be able to compare some of the models that we might build in regression? Then jump into things like moderation, because what I find is that when using multiple regression, just interpretation of main effects is pretty straightforward. But what about when we look at interactions? And so the field has really moved beyond p-values, right? And so when we think about two-way interactions, sometimes two-way interactions can be directly interpretable, but that's mainly, I find, when the 2 variables that you're interacting are dichotomous variables. And so if you have variables that are coded 1, 0, and you have main effects in an interaction, you can kind of infer and look at the coefficients that come out of that model and really be able to say, okay, because these are coded 1, 0, I have an understanding in some ways more readily to think about what the interaction means. But when you start looking at both interactions of 2 continuous variables, continuous and dichotomous, and you start to get to 3-way interactions, it's less intuitive about what it's actually telling you. And so I'm going to kind of show both how you can graph the interactions pretty quickly in multiple regression, as well as how to conduct simple slopes analyses, which really help you isolate kind of regions of significance. So there's going to be a screen that I'll bring over. Chris Preacher has kind of like an R tool that you can interface with. So we'll cover that. And then if there's time, we'll kind of jump into dominance analysis. So 2 of the papers that are there for this week are how to do dominance analysis and why it's actually important. And so what we may do is just jump into it. I'll kind of show you how you do it, what the results mean, and then you can go back and read the papers and then maybe rewatch this video. Dominance analysis is very useful when you're trying to figure out things like predictor importance and you have more than 2 predictors in the model. And then one of the things I think is actually really important and really useful is you've run all these models in R for regression. Is there an easy way to be able to create tables? And the answer is yes. Why spend an hour making an APA formatted table when you can use APA tables? Don't shake your head, Mike. It's incredible. You're wrong. It's great. So APA tables is great for descriptive statistics and correlations as well as ANOVA. So we'll kind of show how to do that. And then sjPlot is fantastic for regression, where you can kind of put a set of models that you build into one table. So that's what we're going to do. So if you want to go ahead and if you haven't, again, just install those packages, and then we're going to call them at different times. So I'm just going to start with loading up Tidyverse. These packages get loaded at the point that we use them. So you could load them right away if you want, but I'm just going to load them where we're going to use them just so it makes sense, at least to me. All right. So Putting that up. So you'll remember from the last few weeks. So I'm switching from the read.csv to read underscore. And so when I do a read underscore CSV, that's reading in the HSV file as a tibble. And so rather than just having a straight table where if you call the data set and it prints everything out, it's reading it in as a tibble. And when you call the data set, it's producing the first 10 cases. And so tibbles are just a nice way to be able to, again, just read in your data to be able to manipulate data. And if you're using the tidy language for doing data manipulations, having everything in read as a tidyverse-based table or a tibble is super useful. All right, so we're going to be looking at different regression models. But before we build that regression model, we typically want to try to understand the variables graphically. And so I'm going to just start with like a simple linear regression. And so we're going to be thinking about the socioeconomic status as a predictor variable and math achievement as the outcome. And so we're going to think about 3 different types of visualizations that we would want to create in order to kind of try to understand what's happening with the data. So one is a scatter plot, and that's what's going to help us visualize the linear relation between the predictor of SES to math achievement. We're then so we can look at linearity. I like to use kind of a smoothing function when fitting the line because it lets me immediately be able to look at whether there's any curvilinearity potentially in the data. And that has implications for when you're, how you model your X variables, and as well as Y, but we'll cover that in another week. We're then going to look at outliers, just creating some simple box plots, as well as ways you can be able to identify the outliers and the values associated with outliers. And then just quickly do some histograms to look at the distribution of our variables before we get into modeling. So a very simple way to be able to generate a plot, and we're going to get into better plots in about 4 weeks from now. I'm giving you things that are very basic. So we're not loading up ggplot. Here we're just using plot functions that are part of the core R language. And so to do that, you can just use the plot language. And what you can see is that when you run plot, you have to specify the data set and the variable. And so you're not just attaching the file, which you could, but we're just going to run a very simple scatter looking at the relation between SES and math achievement. And so the first variable that you put into a plot, it's basically plot open paren X comma Y. So this is plot SES on the X-axis and math achievement on the Y-axis. And so this is going to give you a very simple scatter plot. There are a lot of different things we could do here. We could add kind of a main title here. I think we would do that as main equals plot. Yeah, so apparently there we go. So it did, right? So you can add the title just by doing main equals and then put in quotes what the title of you want your plot to be there. You can also label your X and Y axes. I'm doing this off the cuff, so math. Nope. Did I spell label right? Yeah, that's okay. So that is not the way to do it. There is another way to do it, but I'm not going to go through that now. You can Google that on your own time. So we can get a very simple scatter plot just by running this. And then we can actually overlay on top of that. YLab, thank you. So if we could do YLab equals math. Right, there we go. And then we could actually do the same thing, XLab. Sorry, I'm running off of like 2 hours sleep. It was a long night. So I am a little out of sorts. There we go, right? So now we've got plot and we have math and SES. And what I actually like to do with this is be able to fit like I said, a Lowe's line that will actually kind of smooth out the linear function. What this lets me do again is just be able to see, is there any potential curvilinearity? And just by eyeballing this, you can kind of see that there might be a little bit of a bend, right? It's not too much for me to really think that there is something that I might want to include a quadratic term on SCS. But depending on what your perspective or the way that you choose to model data, right? If it's about kind of prediction versus understanding, if you want to really enhance your R squared in some ways, you might want to put in a squared SES term in there based on the curvilinearity, or at least test that. And in fact, that's going to be something we're going to do just to show how you kind of do model comparisons with multiple regression and R. So the scatter plot looks pretty reasonable. And so we're going to move on to looking at outliers. And so I'm going to kind of use the box plot command here. And so there are a lot of different perspectives on, what constitutes an outlier. For a lot of folks, it's anything that lies outside of like 1.5 times the interquartile range, right? And so the interquartile range is the distance between the 25th percentile value and 75th percentile for that variable. So 1.5 times that difference, anything that's outside of that would be considered an outlier. So here for SES, you can kind of see there's some observations out on the box plot here that may be exerting some excessive influence on the data. So SES has some points we might want to consider. Math achievement looks, relatively fine here. But one way we could specifically be able to identify some of the outlier values is by using kind of this code here. So we're identifying the variable. Here I'm labeling the graph. But then underwards, this is saying kind of underneath paste outliers rows and then use box plot stats. And so this is actually producing this in a list. It's actually retaining the outlier information that's generated by using the box plot command, and it's going to paste it on the bottom of the graph here. And so if I run that, right, you get something like this. So where something like the box plot stat is super useful is where maybe if you have one outlier value, right? Not that there's only one outlier case, but if there is only one outlier value, then it will spit out down here. It will tell you the single value that corresponds to the outlier. And maybe you have 10 or 20 cases. What this is telling us is that there are a lot of different outlier values, which is, again, kind of confirmed by just looking at the plot. So if you just pretended that none of the values were down here and it was only this, you would get one value that was printed down here and it would be, 2.5 maybe. But because we have a lot of outlier values, using this kind of boxplot.stats command isn't really helpful. But what is helpful is that if we know that the boxplot stats is producing these values in something called boxplot stats HSB for HSB SES, and it's being put into this out list, we can actually create this as a tibble. So I'm going to create an object that's called outliers for SES. And I'm basically taking where the outlier information is created and stored, which is right here. I'm basically copying that and making a tibble out of it. Okay. And so if I create that, what this is going to do is give me a tibble of all of the outlier values in the data set. So you can see why down here, it looks pretty funky, right? It's just overlaying outlier rows column values. And it's because there are 14 different values that are considered outliers in the data set. Now, if we wanted to know more than that, right, this is just telling us the values. But because we have 7,000 cases, we don't know how many individuals actually have these values, right? So one of the ways we can do that, let's see if I did this right. You would think I would have checked on my code, but well, let's find out. So we're using tidyverse, where I'm basically using the outlier SES data set. What is this doing? Let's find out what happens. Outlier SES group by value. Ah, yeah, okay. So this here is repeating. Okay, that's what this is doing. So it's actually producing all of the cases. I misspoke. When you generate the outlier SES tibble, it's actually spitting out all of the cases that are considered outliers, not the unique value. So ignore what I said a minute ago, right? Because you can see there's a -2.5 and a -2.5. So it's and another -2.5. So this is just telling you how many cases are outliers. So there are 14 cases that are outliers. if you want to know how many values are outliers, you can actually use this. And so what this is doing is grouping within these 14 values, it's grouping by the value, and then it's saying how many times does that value appear in this tibble. And so if we run this, right, there are actually 9 unique values, right? So minus 3.76 only appears 1 time, which is right there. But minus 2.5 appears 3 times, right? And we saw that a moment ago. 1, 2, 3. And I think that's the same for minus 2.33. So that appears 3 times as well. So you can get the listing of the observations and the total number of observations that have outliers, that are outliers. Then you can also group by value to get an aggregated sense of how many unique values are outliers in this data set. And then you can treat your outliers based on both departure as well as sensitivity through a sensitivity analysis. So you can keep those data in, run your models, and then take those outliers out, or you can just keep them in. It depends on just what your questions are, what the nature of the relation of the outlier is, right? And so is it along the line, is it along the regression line, or is it a departure from that line? And so you would just want to be able to get a sense for how is it, and is it exerting excessive influence on the data? Lastly, we can look at histograms, and so you can just use plot and look at the density. And so if you run that, that is going to give us a histogram with a not so fun title. So we can do what we did before with the scatter plot, and if we just do use the main option, we can give it a nice title. And so it's giving us the sample size, it's giving us the distribution, this is the frequency, and so that can be helpful for a quick look, but it might be useful to have some statistics associated with that. Now you can certainly use some of the statistics commands that exist within R. So if I wanted to do, I think I can do it this way, HSB, SES, oops. So I can type it in there, and I can do the same thing with kurtosis. You can obtain those statistics that way. But depending on if you just wanted to integrate it in the graph, you can also use something like this. So you can have your base plot command, but then you can also paste below, like we did for the outliers a moment ago. You can call other commands and other options in the subcommand. So in this case, it's saying paste the skewness below the graph as well as the kurtosis. And what it's doing here is it's taking the E1071, that's a package that is part of R. And so it's saying round the skewness for this data to 2 decimals. And so using the E1071 with a double colon is calling the specific command within a specific package. So this is saying under the graph, paste skewness, and have the skewness be a value that's a function of the E1071 skewness command for SES and round it to 2 decimals, as well produce print the kurtosis, which is a function of the kurtosis command in the E1071 package, and round that to 2 decimals. So if we do that, you can see we get the same graph, but we also get the skewness estimate that we have here. It's rounded to 2 variables and printed there, as well as the kurtosis. This can be useful for just, again, base plotting. It's useful for both information. It can be useful for sending to colleagues very quickly. So instead of generating the code that produces in the console window, you can have it produced in the graph automatically. All right, so the data looks reasonable. The skewness, the kurtosis, that doesn't look bad to me. And then let me actually plot math achievement. I didn't actually include that in there, so let's do. Here we go. Kind of platykurtic in some ways, but not horrible. I'm not too worried about it. All right, so once you kind of use some of those basic diagnostics to kind of get a sense for normality, linearity, looking at outliers, We can go ahead and run a correlation to get a sense for when we looked at the scatter plot before, what is the conditional mean standardized relation between SES and math achievement. And if we run that using the core command, and so you just do core XY, you can flip it around if you want, because this is a Pearson's correlation, and it's just kind of like a conditional mean based. It doesn't matter what order you put that in. And so the estimate is 0.36. So there's a moderate relation between there's a moderate association between socioeconomic status and math achievement. All right, so that's entirely plausible for us. So now we can go on to estimating the linear model. And so within R, this is just a very basic presentation of the linear model. And so you can use LM for linear model. So it's LM open paren, and then you have the dependent variable. You have the tilting here, and then SES. So this is math achievement regressed on SES, and so that's the regression equation here. And then once your regression equation is specified, you separate it with a comma and you specify the data set. There's a lot of other options that you can include here, but we're just going to start with this for the basics. So if I run that model, we can get an intercept, and we get an intercept value and a coefficient value. So this is a little bit useful, but it is not the totality of everything we would want, right? And so when we've looked at some things before, we want standard errors, we want t-values, p-values, the whole shebang. So what I'm going to do is create an object called C1. And so for a number of these models, I'm kind of like I'm doing it C1 through like C4. That's just for conditional models. So my personal labeling convention, because I do a lot of mixed models, is I tend to do like UC for unconditional, and then I do C for conditional, and then I label things numerically for my object. So that just helps me keep everything kind of sequential and orderly, so I can differentiate between unconditional and conditional models for the purposes that I'm using them. So I'm going to rerun this model, and I'm going to keep it stored in an object called C1, and then I'm going to just use the summary for C1. And now you can see we get more robust information. Right, so we get the same values as before, the same estimates for intercepts and slopes, but now we get the standard errors, we get t-values, we get p-values, and what's nice is that it actually shows you, what asterisks correspond to what levels of significance, which is really nice. And so you also get R squared values, you get F statistics, and there are also some things that are kind of embedded in this that I'll get to in a moment. But I won't show that just yet. So that's very basic functionality for a simple linear regression. It's just the LM. You specify the regression equation here. You specify the data set, and then it's easiest if you just run it within an object. And so by running in an object, you get all kinds of information. Actually, if you expand this here, right? This is C1. So you get fitted values. You get rank. You get residual estimates. There's all different attributes that are stored within this list that you can end up calling for other purposes. And so the larger your models are, the more that you can actually do interesting things with what's in here. So if you wanted to be able to plot coefficient values from this, you can actually harvest that from C1. And so you could call C1 and do all kinds of interesting plotting of the coefficients with their standard errors. I'm not going to show that today, but I could potentially paste that code in for next week, which is just a fun way to be able to show the data in a slightly different way. All right, so I want to return back to a big pile of WOMP, apparently. Oh, let's go like this. There we go. Yeah, so I don't have a clear understanding, so smarter people than me can kind of paste about this, but if your window is too small, you're going to get warnings and errors, actually. And so it's basically saying the margins of the plot are too large and they're not fitting in the window that you've specified. So when I try to run it like this, right, so the figure margins are too large, so it's not going to actually show the plot. You got to stretch it out. And now we get the plot, right? So returning back to this, when we see that there's like, teeny tiny bend that's there. So So maybe from a strict modeling perspective, it might be of interest to see if there is some kind of curvilinear relation, and does that improve our prediction of math achievement? And so do we get any, do we get a statistically significant association? Do we get an improvement in our R-squared by including that? So if we run something like this pretty quickly, we actually get a problem, right? And so it doesn't like what we've done. It's not going to actually produce, like I ran C2, it's not actually going to call that. And so it's saying I've specified SCS times SCS, which would be for SAS users. You can kind of like create those terms within your regression equation. And so for R, we can't just jump right in and create that term there. And so we actually just have to create, that term within the data set first. And so we can do that two ways. One way is we can just say create a new variable called SES2 within HSB, and that's equal to the variable times the variable. So we can do that. The other way is in tidyverse. We can say within HSB create a variable called SES2 that's equal to SES times SES. You can also use the caret and say SES caret 2, so it's to the power of 2. Yeah, that's exactly right. This is being done, it's assuming no missing data. Next week, I'm going to talk a little bit more about missing data and its impact on these models. So for right now, we're just kind of covering, best case scenario, you have complete data. How is it that you run these regression models? We will jump into missing data and how you use that in things like the mice package next week. So thank you for that question. It's a good question, right? Because you might actually think, oh, I'm going to go take this code and use it on my data, and then you're going to get all kinds of red down here, and then you're going to curse me maybe more than you already do. And so you can go back to this video and see that someone asked the question, and then I answered it. No, we're just assuming this is complete data. We're going to talk about how you treat missing data in these models at a later time. All right, so if we create this SES2 variable, now you can see through the tibble, we've got a new SES2. So that's just those values squared. So if I rerun this model, we can just do the second conditional model, which is still regressing math achievement on SES plus a quadratic term, which is the term we just created. So SES plus SES2. So we've moved from simple linear regression to now multiple linear regression. So if we run that and we do the summary, we can look at the results. And so here's what's interesting with that, right? Is if you look at this, you can see that you have a significant linear coefficient and then a significant nonlinear coefficient, right? And so this is kind of telling us that there is a quadratic function, and it kind of like has almost like I don't want to say deceleration effect. Oh, Shrimani, hi there. And so we can actually say that there is this kind of curvilinear relation, and it's a statistically significant term. But here's the issue with this, right? Everything with p-values can kind of get out of whack when you have really large sample sizes. And so in this case, we have over 7,000 observations. And so what this is telling us is that the minus 0.21 is not 0. We can reject the null hypothesis that the confidence interval for this doesn't include 0. And so we might say that that having a curvilinear term matters. But if we actually compare the multiple R squared, I think in the original, what was the original model R squared? So here it's, we explain 13% of the variance by including the term. Here it is 13% variance as well, right? So by adding the term, we go from 13.01% variance explained to 13.07. So we're not really explaining more variance by including that term. So we get a significant effect on a p-value, but we can also say that's a function of the, having nearly 10,000 observations in the data set. So depending on what your kind of statistical training is, you may be more interested in p-values, and that's okay. You may be more interested in effect sizes, thinking about R squared. That's also okay. Another way for us to kind of think about the usefulness of including kind of a quadratic term is by evaluating some information criteria, and we can look at the extent to which our model fit kind of improves by including the additional term. And so we can use the AIC and the BIC. So the AIC is the Akai information criteria. The BIC is the Bayes information criteria. And the idea here is that when you compare these models, you would expect those values to go down. And so if we look at something like the AIC, so the AIC for this model is 47.103, and then it drops by about 2 points when we add in the term. And so one rule of thumb, I think it's Raftery in 1995 published a paper. It's mainly on the Bayes criteria. I think people also broadly use it for AIC, but don't quote me on that. Check it for yourself. And so if there is a difference of at least, I think it's like 5, that's considered like a moderate, practically important difference, where you would retain the model with the lower value. In this case, we're talking about a difference of 2. And so does that matter for us in terms of practical importance? It's that maybe coupled with the R-square suggests maybe we can just go ahead and keep the SES variable and we don't need the squared term. But again, depending on what your training is and what your hypotheses are, this is a way to be able to look at fit of the model. And so you could go with straight p-values. You can use the R-squared. You can kind of like eyeball the information criteria. So here you can see the fit actually gets worse when using the BIC. But you can also statistically compare the log likelihoods between the two models. And so if we do an ANOVA between model 1 and model 2, you actually get an F test for the difference in the log likelihood. This is identical to using, it's the LR test package for those who use that. You get the exact same F. It's chi-square distributed, I believe. So you'll get it as a chi-square in the LR test. And so this is saying there is a significant difference between those models. But it's, again, what is the purpose of your modeling? And so if you're trying to think about R-squared, which for me personally, I tend to be interested in R-squared and then a little bit on the information criteria side, less on the p-values themselves. My sense would be that no, I don't need to include that term, especially if I don't have a hypothesis about it. That's exactly right. And so, the deceleration could be due to outliers in SES. And so that gets back to kind of the earlier discussion of like when you check for the outliers, there were a number of outliers. And so as I think I'd mentioned, you might want to do a sensitivity analysis. And so you can see that some of these parts are, some of these values are pretty far away from the line in some cases. So you might want to look at how things change. But again, if you don't have any kind of theory, you're just including a term in your model, maybe it's useful, maybe it's not. So those are things you might want to consider. All right, so if we now expand this, we kind of included the polynomial term or the quadratic term there. We can add in the other predictors that are in the HSB data set. And so you can, if we add in kind of SES, which is our continuous variable, as well as dichotomous variables here for sex and minority status, we can put that in there. And so this is telling us that all 3 are significantly related to math achievement when controlling for the effects of the other. And so on average, there are differences between males and females in math achievement, controlling for SES and minority status. There are differences between white and minority students controlling for sex and poverty, and then there are impacts of SES controlling for sex and race there. So we may also then want to start exploring interactions, and that would potentially be both theory-based as well as just kind of like data-based, right? These things are fairly significant, and that's just thinking about the precision and the confidence interval around these values. And so you may want to specify interactions. What's great with R is that if, let's say, I wanted to expand all the terms out to where I have 3 predictors, and so the largest interaction term is kind of this 3-way interaction. If I specify just this, right? If I do the model of regressing math achievement on SES times female times minority, it's going to automatically build out every other term in the model. And so you can see you get the main effects for SES, sex, race, as well as the 2-way interactions, and then also the 3-way interaction. And so in this model, it's saying that when you fully expand the model, the only thing that's significant are the main effects. But some folks might not have a specific theory about three-way interactions. Some people might say, well, I have a hypothesis that there is an interaction between SES and sex, and separately SES and minority status. And so you could also build the model this way. You can include two-way interactions. And if you do that, it's going to, again, populate the rest of the main effects. And so you get the SES female interaction, you get the SES minority interaction, and then you also get all the main effects. And so you can see that this is statistically significant, and this one is not. You can also kind of go old school if you desire, and you can just write out all the terms that you specifically want. So it's kind of whatever you want. Okay, so we've built out some main effects models and some interaction models. And what this result suggests, right, is that there's a negative interaction between SES and minority status. It's statistically significant. Because my brain is fried, I don't want to think about the interaction between the continuous variable and a dichotomous variable. I just want to see it. I want to try to understand where is it significant, because the thing with interactions is sometimes they are plausible. Well, the values are statistically significant, but then when you actually plot the data, the number of individuals for whom an interaction exists, it's kind of on the fringe. It's like maybe 3 standard deviations above the mean. So while it might be significant, it may not actually be useful. So one way to actually try to understand the nature of the interaction is just to plot it. And so this is where the rock chalk package is super helpful. So if you want to load that up, what this is going to do is actually plot the nature of the interaction. So what it requires is that you do plot curves, you specify the model that you want to plot the interaction from, right? So even though I've done C4, C4A, C4B, I want to plot terms from C4B. So it's going to take this object and it's going to plot curves from that model. And so it's going to use that fitted regression object. You then decide what is your primary X variable and which variable is your moderator, right? So in this case, what I'm saying is I want to look at the relation between SES and math achievement, and my hypothesized moderator is sex, okay? I'll kind of explain what happens when you kind of flip it, but just for this case, the hypothesis might be the extent to which sex moderates the relation between SES and math achievement. So this mod X vals is basically, it can be a vector of focal values for which the predicted values are plotted. And so that's basically, if you've got if you had a continuous variable here, you can be able to specify, if you didn't want to just do standard deviation, you could specify the different values that you actually want to plot and test for moderation. In this case, because female is dichotomous, using standard deviation, it's just 0, 1. And so that is standard deviation based already. So I can just leave it there by default. Let's see, for interval, I mean, that's an optional command. Those are just intervals that are provided by the linear regression model. You can plot those. And then here I am kind of specifying the label on the x-axis, the label on the y-axis. And then what this is doing here is saying, where do you want the legend to be populated? And so because the moderator is for female, so the x-axis is going to be SES, the y-axis is going to be for math achievement. And so the lines will be for sex, and it's just saying, where do you want it? This is where like R gets a little funky for this particular package. So I'm stretching this out a bit. Actually, you know what? I'm going to show it. I'll show it small first, and then I'll kind of show you what happens. So I'm going to run that. And so you can see this happens, and right, I said bottom right, but it's not actually giving me my legend on the bottom right. It's giving it to the right. So I'm going to stretch this out and keep this stretched at the level that I want. And I'm going to rerun that exact same plot. Now you can see it showing up in the lower right. I want to see what happens if I do upper right. Oh, here we go. I did the wrong one. So let's go top right. And because of the way the plot looks, I'm just going to go top left. There we go. So what's nice about this, right now we've got, so here's SES, here's math achievement, and then these are the predicted values for the relation between SES and math achievement for those that are male, which is the dashed line with confidence intervals, and those who are female, which is the solid line with the confidence interval. Okay, and so what you can see here, and I made a note, is that along levels of SES, you can see that there are points at which the confidence intervals for the two sexes, those lines don't overlap, right? So right here, there is this white space, which is telling us that estimated math achievement at lower levels of SES, the estimated math achievement is higher for males versus females, right? And so this line here, the upper level, the upper confidence, the upper bound of the confidence interval for female math achievement, it doesn't overlap with the lower bound of the confidence interval for male math achievement. But then as you kind of move up and over here, you can see that these lines overlap and their confidence intervals overlap, right? So this is kind of plotting the nature of the interaction such that at low levels of SES, males have higher estimated math achievement compared to females. But for those who have maybe average or higher SES, there are no sex differences in math achievement. And so we can see that in the plot because of the non-overlap of lines here and the overlap of lines here. What we don't have is actually the estimated difference, right? We don't know what the actual estimated difference between males and females are at levels of SES in math achievement, nor do we know what that difference is down here. We can make an inference based on looking at the plot and the non-overlap of lines here that there is a difference. We can also infer that there is no difference here because the lines overlap. So we might say, you know, at what specific levels of SES are there statistically significant sex differences? Remember what I said before, that if you get a significant interaction effect, it's going to show something like this, right? And so we can say, well, out here, there actually is a significant difference. But look at the data points that are out here. There's not a lot, right? And so if you have a significant difference in math achievement at the lowest levels of SES, it's, well, how many individuals in that sample is that being estimated for? Maybe it's like 10. So that's probably at the lowest level of the distribution. Same here, there's no overlap over here, but there's also no one out here. And so those could be some outlier things that are happening. But this shows the importance for why we need to do more of a simple slopes analysis to dig into moderators. All right, I'm going to kind of show the other side of it. So here, the question is, to what extent does sex moderate the relation between SES and math achievement? We can flip that and we can say, to what extent does SES moderate the relation between sex and math achievement? And so you can see here, I've switched the variables and then I'm changing the axis, right? And so, and I'm going to put this top left. So I'm going to stretch this out so you can see the code comparison. So SES is on the x-axis, and it's what we're plotting. Sex was the lines here. Now we're flipping it so that way the lines are going to be SES. And so this is where the values for the moderator matter. Right here, female was dichotomous, so it by default will use 0 and 1 because that is how it's coded. And for SES, because it's continuous, we're going to say use standard deviations, right? And so it's going to use one standard deviation above the mean and one standard deviation below the mean by default. Again, you can specify a vector of values. If you want to go 1.5 standard deviations above the mean, you could specify those in, something like, C, and then specify your variables if it's like -2.5, 0, and then 2.1. Like you could do something like that. But I'm going to go with standard deviations, and I'll talk about the implications of that in a minute. And then run the same plot. And actually, let me do top. Okay, so now what you can see here is that instead of the nice plot, well, I won't say the nice plot, instead of the plot that we had where we had the scatter where we're looking at the relation between two continuous variables, and then we look at kind of like line fit performance based on the dichotomous variable, now it's flipped. And so what we have is sex of 0. So this is estimated math achievement for males. This is estimated math achievement for females. And now we actually have these lines that are for different levels of SES. And so this is high SES. This is average SES, and this is low SES. And so you can see that none of the lines overlap. And so what this is telling us is that kind of along different levels of sex, there are differences among SES, right? So for males, there are differences in math achievement based on SES, right? These lines don't overlap for males. And so we know that for males, higher SES is associated with higher math achievement, and same for females. But we don't have the specific test for here versus here, right? To compare males and females to each other for along lines of high math achievement, we can kind of infer based on what the estimates are and what the confidence intervals are, but we don't actually have an estimated value for that. So I'm going to skip the minority plot for right now because I really want to get to simple slopes analysis. I really want to make sure to cover that in the last bit of time we have. So the way we can move beyond the simple coefficients that we get up here, right? So we can get the coefficient to see, is there something that is significant? We can run these plots to kind of visualize them, but it's actually the computation or the estimation of simple slopes that helps us to be able to unpack what are the actual coefficient value differences along these different levels, and are there regions of significance that actually helps us understand the effects. All right, so I am going to bring up, you can actually copy, if you want to follow along, you can kind of copy and paste that URL into your browser. So that's what I've done right here. Kind of shrink this, move this over a little bit. All right, so when you get to this page, what you're going to see is that it's requiring a bunch of inputs, which come from kind of these results plus one more thing I'm going to show you. And so in these boxes here, if you want to be able to produce simple slopes, it's asking you for regression coefficients. And it's asking you for the regression coefficients associated with the specific interaction that you want to do a simple slopes on. Okay, what I mean by that is, so beta 0 for simple slopes, that's the intercept. Beta 1 is your x variable, right? So like in the plots we just did, we had x equals something and the moderator equals something else. It wants the same kind of thing here. Whatever your x variable is, you're going to put that for beta 1. Beta 2 is the moderator you're interested in, and then beta 3 is the interaction between the focal predictor and the moderator. Now, in something like this where we have SES, sex, minority status, and 2 interactions, you might think, well, which of these things goes where? Well, it depends on which interaction you want to explore. So if you want to explore SES in female, then you're going to use the intercept. That's going to be beta 0. You're going to use SES, female, in the interaction. You're going to ignore the coefficients for minority status and the interaction between SES and minority. Okay. So what you can do for that, if we want to plot that interaction where we're looking at kind of the sex SES interaction, we can start populating that information, and to kind of expedite it a bit, I'm going to kind of do a screenshot of the values you may want to include. Actually, let me do one thing first before that. Sorry. The coefficient variances, I should have explained all this first. So the regression coefficients come from right here. Coefficient variances, those are actually the squared standard errors. Okay, and so for your intercept value, you would put an intercept of 14.23 here. And then the coefficient variance is basically the square of 0.1182. Now you could get out your calculator and do that, where you take each of these and square them. but there's going to be an easier way to do that, and I'll show you that in a second. So coefficient variances are going to go here. Coefficient covariances are going to go here, and I'm going to explain where you get that as well. And so what you're going to want to put here is the covariance between the intercept and the moderator. That's going to go in this box. And then you're going to want to put in the covariance between your focal predictor and your interaction in this box. I know that's weird. I'm going to explain in a second. I'll show it in a second so it makes sense. And then here's where you're going to put the conditional values for your moderator. And so in the case of SES and sex, we're going to actually put SES in the Z box. We're gonna treat SES as the moderator, and so that's so we can be able to look at the standard deviation lines like -1, +1 standard deviations around SES, and then sex is going to go here. All right. So where we get the coefficient variances and covariances very quickly is we can use this command right here. So when we run the regression analysis, again, we put that in an object C4b. If we do vcov C4b, that is actually going to produce a variance covariance matrix in it. There we go. It produced it. Didn't like something I was doing, but I don't care about that right now. So what you can see here is along the diagonal is the coefficient variance associated with each coefficient, right? So think of it just like a typical variance covariance matrix. This is the coefficient variance associated with the intercept. And in fact, if you take what was the coefficient standard error for intercept? If you take 0.1184 and you square that, you get 0.014, and that's what you get right here, right? So same if we take SES and I take 0.156 and I square that, I get 0.024. So if I go to SES and I follow along to where it is on the diagonal, right, you get 0.024. It's right there. So the diagonal are where you can find the coefficient variances, and then the coefficient covariances are on the off diagonal, right? So right here, this is the coefficient covariance between intercept and SES. This is the coefficient covariance between intercept and sex. This is the covariance between intercept and minority status. So we can take this matrix and populate those values into these different cells. And so what I'm going to show you here is this is basically what you would end up putting in if we wanted to look at the interaction between minority status and SES. We can put those values like this. So I'm just going to actually populate that here so we can walk through this. So I'm going to put in those coefficients here. So minus 2.95, 2.72. So this is the value for SES, because I'm going to treat SES again as the moderator. That's going to be the Z. The values are going to go there, and I'll show that in a minute. Then I want the interaction terms, which is minus 0.56. The coefficient covariances, again, I can pull that here. So it's 0.014, 0.003, 10. Whoops, is that right? Yeah, well, so minority status. Here we go. It's actually, there we go, right there. So we move that over. So it's the 0.003107, 0.024 for the 2.72, which is, right, so that's SES. So that's right there, the 0.024. And then for the interaction term, the coefficient covariance is 0.043, which is kind of right there. I'll just put it as 0.044. Okay, so we have the coefficient, those are the coefficient variances. Now the coefficient covariances, in this case, this is between the intercept and the moderator. So in this case, the moderator is SES. And so I want the coefficient covariance between intercept and SES. So if I come over here, the covariance between intercept and SES is minus 0.00314, which is right here. That's the beta 0, beta 2 covariance. Here, the beta 1, beta 3 covariance, that's the covariance between minority status and the interaction term, which is right here. So that's minus 0.008168. And you can go back and watch this, and hopefully, that will help make this a little bit more salient. What I want to do now is put the points that I want to plot and be able to test. So my x variable in this case, remember, is the dichotomous variable. That's for minority status. And so that's 0 and 1. But for the values that I want to put for SES, I need to know what the mean and standard deviation are for SES. So in this case, the mean of SES is 0. So I can put that right here. So the 2 value is for the mean. This value here is for 1 standard deviation below the mean. So because the standard deviation is 0.779, I can do minus 0.779. And here I can do 0.779. So this is the way that you can populate all the information. And then you actually want to put in your degrees of freedom, which is 71, 79 in this case. So if you populate all of that information, this is going to do a simple slopes analysis. So you can actually then hit calculate once all of this is in here. And it's going to kind of give you all of your input information. All right, so then I want to align this to see if this is going to help us make sense of the graphs we saw before. Oh, I did minority status, didn't I? So I actually need to run that model. My apologies. All right, here we go. Okay. So what this is saying is at low levels of SES, okay, so CV1, which is a standard deviation below the mean of SES, which is this black line right here. So what this is telling us is that there is a statistically significant difference between minority students and white students in their estimated math achievement at a standard for individuals who are a standard deviation below the mean in SES. So it's telling us here that this value right here, so these are minority students, these are white students, this is the math achievement. This is saying that on average, for individuals who have low SES, minority students have lower math achievement, it looks like, than white students. And this is saying, yes, on average, it is about 2.5 points lower than for white students. And so you can see that this is about 12, and this is about 2.5 points lower. This right here is telling us, or testing the difference between minority and white students for individuals who are at the mean of SES. So for this line right here, it's saying that this value right here is statistically lower than this value right here. And then in the same way, at high levels of SES, which is the green line, so here's the intercept of 16, which is here, it's telling us that minority students perform about 3.5 points lower than white students. And so the difference between this value and this value is statistically significant. So that's what this type of calculator does, is it's not just an eyeball. It's not just about overlapping or non-overlapping lines. It's giving you specific hypothesis test information about along different levels of your focal predictor or your moderator, are there significant differences in math achievement? And you can use this to both compute effect sizes as well as just be able to have more information about for whom is something statistically significant or not. I have a couple other examples in here. Again, I know that's a lot to take in a short amount of time, but I would go back, and if you want to be able to kind of like watch this again and be able to see kind of how that process goes. I'm also going to upload like those screenshots of what I showed. So you know what values you should use. So I have, female and SES simple slopes. I'll put these pictures up there so you can be able to practice it on your own time. It is 2 o'clock, but I really want to show the last couple things, which is what do you do once you have information? And so if you need to go, thanks for coming. I'll probably spend maybe just like 5 more minutes, 10 at the most, of just kind of showing what you can do in terms of simply creating tables. And so this is where you can use the apaTables for creating just like quick correlation descriptive statistics. So if you call that very quickly, one of the things you need to be able to do in order to get that table to look good and perform right is you need to just retain the variables that are of interest. And so because the HSB data has IDs in there, if I was just to use HSB, it's going to produce correlations between the ID variables and these other variables as well. So here what I'm doing is just the tidy, from the tidy work we did before, where I'm saying select everything but the student ID and school ID variable. So I'm saying create HSB1 from HSB and then select everything but the 2 ID variables. And so if I do that and then use apa.core.table, what you do here is just call HSB1. I'm actually going to get rid of this because this command has been deprecated. So you do apa.core.table and you can specify a file name. And if you run that, I'm going to show you what that looks like. It's exporting a document out. There we go. And so now you get a nice quick little table. It's producing confidence intervals underneath. You can just quickly delete those if you don't like them. But it flags, it gives you a table note by default. So this is a very quick way to be able to get means and standard deviations, which I think it's pretty nice. It takes less time to format, I find. And then the last thing you may want to do is be able to create quick tables for regression models. And so that's where you can call the sjPlot package. And it's very simple. You basically take all of the models that you want to include in a table, and you can do it as simply as this. So remember, we did a whole bunch of conditional models with 1 predictor, with 2 predictors, with 3, 4 interactions. If I want to put all of that in one table, I can just do tab model, and then here's where I list all of the different regression models I want to put in the table. Well, I highlighted it, so of course that's going to be wrong. So if I run that, it produces this. And so this is giving me a kind of nice table. This isn't too helpful because it's kind of in an HTML format that's showing up in the viewer. So what I can do instead is kind of throw it in a file. And so I can do, where is it? File equals go, and oops, I did .docs. Let's do .doc. All right, so you can actually get something if I flip the layout a little bit. I can do some things here where now we're starting to get information. You need to format it a bit, but we're starting to get we get everything kind of synthesized somewhat easily. Now that's still not great, right? Because there's things like, I don't know what model this is. These things aren't labeled too well, but you get all the information in one place. A quick way to work around that is there are a lot of options within tab model. So here I'm basically using the same type of command. I'm just adding on to it. So what I'm saying in here is create a table that's still a function of all of those objects, but remove the observations. I don't need to see the observation shown. You can remove the confidence interval because I really don't care about the confidence interval. And so show that equals false. But instead, I want standard errors. So what I'm saying is remove the observation number, remove confidence intervals, show standard errors, call standard errors SE. By default, it will do like STD error, and I don't want that. That's too bulky. Here, I'm saying don't bold the p-values. I don't care about having things that are less than 0.05 put in bold. I'm also saying round the p-values to 3 values. And then I'm actually labeling the dependent variables, right? So what this is doing is putting just by default math achievement as the dependent variable for every single one of these. But I want these labeled according to the model. So I have 5 models printed. I want to have those models labeled accordingly. So I'm just listing those across, and you want these to pair to this. So if this is your first model and you want to call it model 1, call it model 1. You can really call it whatever you want. But if you label it that way, it's going to come out that way. Then you can also label the predictors. And so what I tend to do is run it this way first. I run it without the predictor labels so I can see the ordering of the predictors. So here I see it's, you know, intercept, then SES, then SES2, female, minority, all the way through. So now I can give some better formatting to the table. So you can see I've removed the parentheses from intercept. I've capitalized some things. So if I run this, I'm actually going to get a much nicer table, right? And so if I stretch this out, this is much more aligned to an APA type of table. And then you can do the same thing as before, where I could just export this out. I can do file equals, reg2.doc. I'm going to bring that up. You can see that. And then I'm going to change the layout, landscape. And so now it's looking much better, right? There's formatting you're going to want to do with the margins a bit to get it all into one page. Clearly, it doesn't want to work with me right now. You get the idea. And so you can format these things on your own. But this is a nice, quick and dirty way to be able to get all of the information from your regression models into a table and not spend, you know, 30 minutes to an hour trying to put together a table. So those are a couple quick and easy ways to be able to get your data into tables for reporting purposes. We're out of time for this week. So what we're going to do next week, this is actually going to be fun. So next week, we're going to jump into dominance analysis. So if you want to read those papers, that's great. And then I'm also going to talk about quantile regression, which is, that's, if you're not familiar with it, that's something that I've been publishing on in kind of like Head Sciences for a while now. It's a different type of way to think about kind of conditional means-based modeling. And so all of our regression models are conditional means-based. We're going to talk about kind of conditional median and conditional tau-based models. So more next week. I'll actually add a quantile paper up there if people are interested in on the text you're working on for quantile regression. Yeah, so I'll put some things up. I have an app as well for, it's a Shiny app for quantile regression. I'll maybe show that as next week as well. So, okay, so thank you for coming. We will see you next week. I will get the video up soon. I hope this was fun, useful. It wasn't as funny this week. I realized I didn't do anything that was super hilarious, but maybe you're not here for the dad jokes. So thanks for joining. I'll put the video up soon and see you next week.